today we want to generalize this power counting we did on video 10, applied to lambda phi n theories, to more general theories that can be comprised of scalar fields, spin half fields, and vector fields, right? With also more general interaction between them. So now we can have not only more fields, right, different fields in our Lagrangian, but also more than one interaction between those fields. In order to do that, we'll have to also generalize some of these variables we were using before to characterize our diagrams, right? So before we had this kind of topology for a diagram expressed in four numbers essentially, right? The number of external lines, which I called n, the number of propagators, which I defined as p, and the number of vertices that I defined as v, and also the number of loops, right? Now that I have many fields in my theory, I have to say also not just the total number of legs, but how many of those legs belong to each kind of field in my Lagrangian. So I'll call that number nf, and usually I'll be summing over the f to cover all the fields in my Lagrangian. The same for the propagators, right? And for the vertices, I will use a different numbering, right, to keep track of the different interactions, because even between fields of the same kind, I can have more than one type of interaction. So say, even if I have just a scalar, right, I could have a theory that has a lambda phi 3 plus a phi 4 plus a phi 5, you know, different powers of this field, so different interactions, right? Also, the interactions will be characterized by a few numbers, right? Given one particular interaction in my Lagrangian, I have to say what kinds of fields are involved in that interaction, and that will enter through a set of numbers which I'll call NIF. So for each interaction, I want to know how many lines, right? The interaction will be translated by Feynman rules into a vertex, right? And I want to know how many lines of each type of field go finish, right? Have endpoints in that vertex, right? Say, think QED, right? QED has two fermions and one photon coming out of any vertex. So this will be given by a set of numbers like that. Also, I want to know for each interaction how many derivatives are involved in the interaction, right? We know that it's possible to write derivative terms in the Lagrangian, right? And that those derivative terms introduce powers of momentum, right, in my vertices. And of course, that's important. These powers of momentum are important for my power counting, right? If I want to know if diagrams are converging or diverging, that's an important piece of information. Let me give you a couple of examples just to make these more definite, right? So take an interaction Lagrangian that looks like this. Minus IE del mu phi star A mu phi, right? Phi is a complex scalar, A mu is a vector, right? And another interaction which is minus lambda over 2 factorial square phi square, right? This is a scalar QED interaction term. It's not the full interaction, but just one part of it. And this is what looks like a lambda phi 4 for a complex scalar field. In this case, I have two interactions. So my interaction index here has two values, which I'll label by the coupling, say this electric charge here and lambda. And I have two types of fields. I have the scalar field and the photon, right, for scalar QED, which I'll label by gamma. Right? And that means for the first interaction, let's say E, right, I have these numbers, right? So I have N for the interaction E field phi, which is 2, because in this interaction I have two lines for the scalar field. I have n e gamma, which is 1. So the vertex looks like this, right? For this interaction. And of course I have a derivative here. So dE is equal 1, right? So these three numbers characterize the first interaction. For the second interaction, which I labeled lambda, I have n lambda phi. It's just 4, because this looks like a phi-4 theory, right? N lambda gamma is 0. There's no photons on this interaction. And the number of the derivatives is 0, right? So you can see I can, just by looking at these parameters here, I can fully characterize the interactions as far as what I want to know here, right? Which is the important things for power counting. Just to give another example, let's take a look at QED, right? In this case, with just one fermion, right? The interaction Lagrangian looks like this, right? A mu psi bar gamma mu psi, right? So two fermions and a photon. So in this case, just one interaction that I will label by E. And there's two kinds of fields, right? The fermion and the photon. Right? And in this case, pretty clear, right? It's very similar to the scalar QED, at least for that interaction in scalar QED, in which the number of fermions is 2, the number of photons is 1, but in this case there's no derivatives, so the E for this theory is 0, right? So you can see by these two examples how I can describe pretty much any interaction, right? Again, as far as power counting goes. Now, what I want to do, right, following exactly what I did in video 10, right, is define the superficial divergence, right? I want, again, to define D, right? In the case of the lambda phi n theory, this was just dl minus 2p, right? Where d is the number of space-time dimensions, L is the number of loops or undetermined momenta, right? The number of integrals in momentum I have for any diagram, right? And P the number of propagators. I don't want to generalize these to the theories I have above, right? The part where I count the number of loops, it doesn't matter what kind of loop I have, just how many integrals in momentum I have to do, right? And how many integrals in momenta I have for each loop, which depends only on the dimensionality of space-time. That does not change. So this term still dl. I still have L loops, and each of those loops will contribute d powers of momentum. Again, in that region, remember from video 10, where all momenta are going together to infinity, right? Now I have to say about the rest, right? So one of the next contribution here, which was 2p for a scalar field, is related to the propagators. And it came from the fact that each scalar propagator put 2 powers of momentum in the denominator, right? Now I have to be more general about that, right? And we have basically two cases here. One for bosons and one for fermions. So we know that the scalar bosons, the spin 0 boson, contribute something like 1 over k squared, right, in the denominator. That is also true for massless spin 1 bosons, right? We have seen in quantum field theory 1 the propagator for the photon, and it's just like that, right? And maybe you're already seeing this somewhere else, maybe not, but you have to believe me that even in the case of non-abelian gauge bosons, and more generally, even massive spin 1 particles, right? This is still the case, right? Still we have a contribution that is 1 over k squared, right? We'll eventually do non-abelian gauge theories and see that explicitly further down these very playlist, right? But also maybe eventually we get to spontaneous symmetry breaking and take a look at massive spin 1 particles. Probably not in quantum field theory 2, but now I can start promising things for quantum field theory 3, right? Well, now fermions are a little bit different, right? Fermions have a k slash in the numerator, right? So effectively, they provide one less power in the denominator than bosons do, right? One way to put these two things together is to write propagators like that, like k squared minus 2s as in spin, right? It's not really the spin, but I'll use this variable f as f, right? To specify the field, right? And define this SF so that this guy is equal to 0 for bosons and half for fermions, right? That way, the propagator will behave like it's supposed to behave for each of these two kinds of particles, right? And again, all I worry about here is power counting. Of course, there are other terms here, but I'm also always thinking in the limit that these loop momenta are going to infinity together, right? With that in mind, then the contribution from propagators, right, coming from here, will be, for each propagator, I'll have a negative power like that, right? So in the numerator, it would be contribute like a power of moment that is 2SF minus 2, right? And I have to sum over all propagators for each kind of field. So I put PF here. Remember, PF is the number, if I look at the diagram, PF is the number of propagators for the field F, right? And I have to sum over all fields in my theory. So for each diagram, I have this total power coming from propagators, right? So I'll put that up there, right? So now my D is given by, let me get some space, plus this, plus something else that I'll discuss in a moment. But you can see that in the limit that I have just one field, F, and that's a scalar, right? So SF is 0 because this is 0 for bosons. I go back to that minus 2p that I had before, right? So that's okay. Now, I'm also, before that was all, right? But now I'm also opening up the possibility that I have derivatives in my interaction. And derivatives, of course, provide a power of a momentum in the numerators, right? If you have derivatives in interactions, their vertex will depend on the momentum of the fields going in, right? So each derivative will contribute with one power of momentum. That means that in a vertex that I have d derivatives, and remember I define this variable di, which is the number of derivatives entering for the interaction of type I, right? If that will mean d powers of momentum in the numerator, but I have to multiply that by the number of vertices of that interaction, right? If I have 3 vertices and each of them involves 3 derivatives, I'll have a total of 9 powers of momentum coming from that. And of course, then I have to sum over all the interactions in my theory, right? For each of them, I see how many vertices appear in that particular diagram and multiply by the number of diagrams. So this is the contribution from propagators. And now this is the contribution from derivatives in my Lagrange. In interactions, of course, right? I'm not talking about the derivatives in the kinetic term. And that means now I have to also add this contribution to the superficial divergence. Let me put it here. And that's the expression I was looking for, which is the basis for the rest of our analysis today, right? So I have a superficial divergence that is now, in pretty general terms, given like that. Now, you might remember from video 10 that this is not really the form of the superficial divergence that is very useful to us, because what we're really interested in is to look at n, big N point functions, right? N, big N here is the number of external legs, right? And we want to know what happens to this as I increase my perturbative expansion, right? As I go to higher powers of the interaction, and that means bigger number of vertices, right? So I want to really express this as much as possible in terms of the number of external legs and the number of vertices, right? And that I used a few topological relations that came from the structure of diagrams. One of them was that I could write the number of loops, right? And that means the number of undetermined momenta, right? In terms of the propagators, right? Because each propagator introduces one momentum, minus the number of vertices, because the number of vertices means also the number of momentum conservation relations, right? Dirac deltas. Minus 1, because in the end, there's one of these momentum conservation delta functions that is just the total momentum conservation. So I got a relation that looked like that in video 10. Now that's still true, right? That's still true. With the caveat that here I have many different kinds of propagators, so I have to exchange these. Let me bring this one to the front here, right? And I have to sum propagators that now can be of field type F over all the field types, right? So I'm summing the total number of propagators. And the same is true for vertices, right? Now vertices can belong to any particular interaction, and this is the number of vertices of interaction I, and I have to sum over I, right? So this is really the relation I'm looking for now, right? Which is equivalent to the one I had before, and I can substitute that right here. I can exchange L by this expression here, and then simplify a little bit, right? That's just algebra, and what I'll get is d is equal to d space-time dimensions, right? This is just d times 1 from here. D times this term I'll group with the propagators here, so I'll get the sum over f of pf times this 2sf minus 2 plus now contribution from here, so plus d. And then the d times this I'll group with this part, so I get plus the sum over I of vi times di minus d. Don't be confused here, right? di is the number of derivatives for this interaction, and just d is the number of space-time dimensions. Okay? So that improves a little bit my expression for the superficial divergence, but still not what I want, right? I want these in terms of external legs and vertices. In order to do that, I'll do again something very similar to what I did in video 10, right? So in that case, I had only lambda phi n theory. So each vertex produced any lines, right? And I wanted to relate the number of lines that come out of vertices to the total number of lines in the diagram, right? And they need to be the same, right? And I kind of proved by induction that these needs to be equal to these, right? You start with, I don't know, just external lines, right? So NV equal big N, right? And then you show that every time you take two of these external lines and connect them together, you're taking out two external lines and adding one propagator. So the proportion between them needs to be N plus 2P. Now this is still true, right, for any particular field. So if I take just any of these types of fields in my Lagrangian, it's still true that the proportion to between external lines and propagators is this one, right? If I remove one of these propagators, I have to break an internal line, right? And break a propagator to put two external lines, right? But now I have many kinds of vertices that can produce this field F, right? So I have to sum over all the interactions in my theory, right? And for each of these interactions, I have to see how many lines of this kind of field can come out of that vertex, right? So, and that's NIF, right? So again, I'm counting on the left-hand side how many of lines of this kind of field is coming out of each vertex, right? Summing over all the vertices in my diagram, right? All kinds of interaction. And for each interaction, I'm counting the number of vertices, right? And that needs to be equal to the total number of external lines plus twice the number of propagators because of this proportion, right? So that's the relation I want, right? Again, it's pretty generic to any kind of interaction, right? And I'll have one equation like that for each kind of field in my Lagrangian, right? This I can rewrite just isolating the propagator here. PF will be half of this sum here minus NF, right? And this expression now I can use up here, right? I can take my expression for the superficial divergence and substitute this number of propagators by this whole expression, right? Then there's a little bit of algebra. You have to multiply and rearrange stuff here, but pretty easily you can see that you can rewrite now the superficial divergence as D minus a sum over interactions, because I'll group everything that is multiplying VI right here as a sum, right? And that defines for me the coefficient of VI. Again, I'll call delta, but in this case, delta is different for each interaction, so I put an index I. Before I had an index N, that just mean phi n, right? The only kind of interaction I had is phi to the power n, so I was characterizing it by n. Now I'll do it more generally, right? I is just any interaction, right? Vi. And then you have the part which is the coefficient of the number of external legs that enter here through this term, right? And you have this coefficient in front, right? And that is a sum over all kinds of fields, right, of SF plus D minus 2 over 2 NF, which is really what I was looking for, right? Now I have expression that is fully written in terms of the number of vertices, the number of sternal legs and some intrinsic properties, right? Like the size of the space-time and so on, right? So let me put a box around this because it's really what we were looking for. And let me write the definition of delta in this case, which is a little bit more complicated than before, right? This is dependent on the interaction, right? And of course, the properties of space-time. So this will be given by D, right? D is space-time dimensionality, di, the number of derivatives in the interaction, minus a sum over f of NIF times SF plus d minus 2 over 2. And you can check that this definition of delta and these also this definition of the superficial divergence, if you're talking specifically about phi n interactions, you go back to the definitions we had in video 10. They're all the same, right? And in fact, even the expression for the superficial divergence is not that different, right? You can see that unless you go to really low dimensions, right, this coefficient is positive, right? And again, the behavior as I go through the perturbative expansion will be dictated by delta f or by delta I, right? Depending on delta I being positive or negative or zero, right? I see that the degree of superficial divergence, right, increases as or decreases as I go to more and more complicated diagrams, right? As I go through my perturbative series. Now let's see a few examples, right? Let's take a look at some of our favorite theories. Right? Let's starting with the best of them all, QED. So in this case, for the simplest incarnation of QED, all I have is this interaction. So I'm putting just one photon and the electron, right? Which is represented by this fermionic field here. Also, I'm thinking now 4 dimensions, 4 space-time dimensions, which is our favorite number of dimensions, right? And so I have just one interaction, which I'll give this index E, right? And 2 fields. We already saw that in this case, right, I have this N E psi equal 2 and E photon equal 1, and the number of derivatives is 0, right? And of course, I have this spin variable here, which is it's not really the spin, again, it's just this to keep track of how the propagator behaves, and it's half for the electron and 0 for bosons, and that includes the photon, right? That means now that delta, I just plug these numbers up here, right? And you see that delta is 4 for the number of dimensions, right? No derivatives. And now I have to sum over field types, right? So let's start with the electron. NIE is 2 times half plus, right? D is 4, right? 4 minus 2 over 2 is just 1. And now the other term in this sum is the photon, right? So minus NE photon, right, is 1. SF 0 for the photon. And again, this is just depends on space-time, is 1. Right? So we have a 3 here, right? So 3 halves times 2 is 3. There's another 1 here. So 4 minus 4, delta E is 0, right? Which means that I can increase the number of vertices in my theory, in my diagrams, right? I can take a particular endpoint function that fixes the number of sternal legs. as I go through the perturbative series, increasing the number of vertices, right, the degree of divergence does not increase. So I have a finite number of different divergences, right? And that theory is renormalizable. So again, delta equals 0 means that the theory is renormalizable. In this case, I just have these interaction in my theory, right? So now there's a shifting language, right? Before, and even in the case of QED, we are always talking about a model, really. I keep saying theory, but the Lagrangian is really a model, right? The theory is quantum field theory, but the Lagrangian is the model, right? That has only one interaction. In the case of phi n, I did that. In the case of QED, it's just this interaction, right? And then saying the interaction is renormalizable or the model is renormalizable is the same thing, right? Now I can have more than one interaction, so I'll have to refine. What I'm finding here is that this interaction is renormalizable. Let's look at a different, another example, which is also a very important one, which is the Yukawa interaction, an interaction between fermions and scalars, right? Usually we write it like this. Sometimes people use G for the coupling. I like Y for the coupling. But the interaction is just psi, psi, phi. Psi bar, psi, phi, right? So now again, I have only one interaction, which I'll call Y. I'll label Y. And two kinds of fields, which are now a fermion and a scalar, right? Just by comparing these two, you see the situation is really similar, right? And just replace the photon by the scalar, and you see the numbers are all the same. I can just copy all of these. Go down a little bit, right? And then just replace here, right? By the phi, replace all the e's by y's. There's also no derivatives, two fermions, one scalar, and S for the scalar is 0 too, right? So I don't have to do everything again. It will be exactly the same calculation. Again, I'm in 4 dimensions. So you see that we found another renormalizable interaction right here, which is the Yukawa interaction, a very important one. Not only was very important in describing nuclear physics at some point, but also nowadays that's how the Higgs interacts with all the fermions in the standard model. So it's pretty important interaction. Now for another example, let's take a look at the Fermi interaction, which you might be familiar or not, right? But was very important in describing weak decays in the earliest days of the standard model, right, of the weak interactions, also in 4 space-time dimensions, right? This theory is an interaction characterized by this coupling GF, G Fermi, right? And it has like this 4 fermion structure. So you have 4 fermionic fields, right? And gamma, this big gamma here, not to be confused with the 1pi functions, is some Dirac matrix, right? Or combination of Dirac matrix. So a particular example could be gamma mu here, in a way that all the Lorentz indexes are contracted, right? You don't have any strength stuff. But it could be more complicated stuff like gamma mu, gamma 5, and you know, right? That's pretty general interaction, and you had many of these currents, right? You had neutral currents, charge currents, you name it, right? And for this interaction, we have, again, we want to know this. Now there's only one kind of field, only one kind of interaction, if you forget about the gammas, right? And NF psi is 4. You have 4 fermionic fields. You have no derivatives, right? And S psi is 1/2, right? You plug those in that expression I had for delta, and you find out that delta F is minus 2, right? Which means, if I look back here, that delta is negative. That means you have a total positive coefficient here for the vertices. And if I increase the number of vertices, I can make any endpoint function divergent. So I have an infinite number of different divergent endpoint functions, and so the theory is non-renormalizable, right? And that's a pretty important example, right? Because as I said before, non-renormalizable theories are not just useless things, right? As I said, this was a very important theory in describing early in the development of weak interaction, right? So we'll comment a little bit on how that is possible with infinite amount of renormalization conditions needed. How is it possible that such a theory can work on the next video? So I'll make a video and I'll use the Fermi interaction as an example. So bear with me and we'll see a little bit about this, right? Now, again, I have the same classification as before, right? Usually, what I'll do is separate interactions between those that have delta I bigger or equal to 0, right? And if every interaction in my model is like that, suppose all the interactions, I put many interactions there, I calculate, I figure out what delta I is for each of them, and they are all either renormalizable or super renormalizable, which is the case where delta is bigger than 0, not just 0. If everyone is renormalizable, then the model itself is renormalizable. Right? Now, if any of these interactions is non-renormalizable, that means that the whole model is non-renormalizable, right? So I'll use that language now to separate which interactions are renormalizable or not, and then the whole ensemble of interactions determines if the model is renormalizable or not, right? And I gave here a few examples, right, that show that QED, Yukawa are renormalizable and Fermi interaction, for fermion interactions are not. As before, doing a little bit of dimensional analysis here will give us more insight on what is really important for this whole renormalizability property, right? So let's take a look at the dimensions of fermionic and vector fields in d dimensions. Right? So I can get that, as I did for the scalar field, by looking at their kinetic terms. So if I look at the dimension of psi bar del slash psi, right, which needs to be d, because every term in the Lagrangian has to have dimension d, right? I can figure out what's the dimension of psi, right? So this is just twice the dimension of psi, because I have 2 powers of psi here, plus the dimension of the derivative. Let me fix this, which is just 1, right? And that needs to be equal to the number of space-time dimensions, right? Because remember, the action needs to be dimension 0, and that means the Lagrangian needs to have dimension d. I can solve this equation here and get the dimension of psi is equal to d minus 1 over 2, right? So that's the important piece of information I was looking for. Right? You see that in 4 dimensions, fermionic fields have dimension 3/2, right? Now, I can do the same for the vector field, right? Just take the kinetic term for a gauge boson, right? This is dimension. There are many pieces here, but they all have the same structure, right? This is something like del A, right? for some Lorentz indexes here, mu, nu, alpha, beta, right? I have more than one combination possible in here, right? But the dimension is the dimension of these, right? Which again is twice the dimension of the vector field plus the dimension of derivatives, which now I have 2, right? And again, these needs to be equal d, which means that the dimension of A mu is d minus 2 over 2, right? Now, I want to do dimensional analysis for this, and it's very useful to put these two things together, right? So I can rewrite this guy using that same spin tracking variable that I defined before as this, right? d minus 2 over 2, because then if I put 1/2 here, I go back to this. And I can use exactly the same expression for this one, right? Because of course, in this case, SF will be 0, right, for the photon. And now it means that I can write the dimension of any field, for spin 0, 1/2, and 1, like this, right? Just using the definition I used before for SF, right? Now, I know that in the Lagrangian, I can write any interaction as an operator times a coupling constant, right? So if you take your Lagrangian and write all the free terms of your Lagrangian, the Gaussian terms, right? The terms that are quadratic on each of the fields, right? Plus interactions which are not quadratic in the fields or higher powers of the fields, you can sum over all the interactions, right? Again, this I run over all the interactions in my theory, right? I can rewrite all the interactions in this form, just Gi times an operator. So I'm putting all the fields here, and whatever numbers that appear in front of them, be it GF, lambda over 4 factorial, whatever, this is all inside this G. In here I have the fields, right? If I want to know the dimension of these operators, right? So the dimension of operator I will be given by these many numbers that I said that characterize the interaction, right? So clearly there's a contribution from derivatives, right? So each derivative contributes dimension 1. So the total number of derivatives is di, so this will contribute with power di, right? And there's also a contribution coming from the fields in that operator. So I have to sum over the fields that appear there, right? And the dimension of each of those is the kind of field. So let's represent the field in the operator by phi f, right? So this can be the photon, can be a fermion, can be another vector boson, can be a scalar, you name it, right? But this is raised to some power in that operator, and that power is NIF, which I defined before, right? This is the number of legs of field type F that come out of interaction I, right? And that means that field F needs to appear to power NIF in the operator, right? So now I just have to rewrite this in here. This is just di plus this comes out as a multiplicative factor, right? Sum over F N I F times the dimension of field of type F. But I said I can write basically the dimension of any field like that, right? In fact, the scalar field, we have seen it in video 10, has also dimension d minus 2 over 2. So this expression is also valid for the scalar field. So let me put that here as F plus d minus 2 over 2, right? Now, I also know that the dimension of gi times the operator, since this is a term in the Lagrangian, right, needs to be d. And that means that now I can use the dimension of the operator here in this expression, right, and write that the dimension of the coupling in front of the operator is the dimension of space-time minus the dimension of the operator, I. And that, if you go back to the definition of delta, is exactly delta I, right? Delta I was really, let me find it, the dimension of space-time minus this. And this we have found now is the dimension of the operator that generates that interaction, right? So going back down, I have this, which is very important result. And also this one is pretty important and worth remembering. So what we're seeing now, that very important thing, right? If you want to know if an interaction is renormalizable or not, what you need to know is the sign of this guy, if it's bigger, smaller, or equal to 0. And where do you get that from, right? You get that by comparing the dimension of the operator that generates it, and that's easy to figure out if you know the dimension of the fields themselves. You're just multiplying fields, right? And you compare the dimension of the operator with the dimension of spacetime. If the dimension of the operator is bigger than the dimension of spacetime you're working with, then delta will be negative, right? And your interaction will be non-renormalizable, right? So higher dimension operators lead to non-renormalizable theories, right? And the opposite is true, right? The lowest dimension operators are the safest ones from the point of view of renormalizability, right? And again, as we have seen already for lambda phi n theories, right, the dimension of the coupling is the same as this delta that appears multiplying the number of vertices in the definition of the superficial degree of divergence, right? So you see that everything that we talked about in the case of the scalar theory generalizes pretty smoothly to more complicated theories, right? And that's what we wanted to see today. Thank you for your attention.